Alright, so here we have a good circuitry question that is going to force us to discuss rather than just calculate how brightnesses of light bulbs change as we sort of open and close a switch. Alright, so the first thing we have to do is calculate the current in bulb A with our switch closed. So redrawing the circuit, I can actually do that. That's one of our loops. Then we have our switch, which is closed, so current can flow through. Alright, I'm just going to label these like that, and then put the values. So 9 volts, 3 ohms, 6 ohms, and another 3 ohm resistor. Okay. So, to do this, to know the current through A, since A is in series with a battery, that's the same as asking what's the current that comes out of the battery. And if we want to know the current that comes out of the battery, we need to know the total sort of equivalent resistance of the circuit. So the first thing I see when I want to do that kind of thing is that these two are in parallel. Whatever the potential difference across bulb B is, it has to be the same as the potential difference across bulb C. That's a definition of parallel. So I'm going to combine those two bulbs in parallel. So I'm going to call that RBC. The combination of those bulbs is going to be 1 over 6 plus 1 over 3 to the negative 1. Right? And I can do a common denominator to get 1/6 plus 2/6, which is 3/6, and then I invert that to get 6/3, or 2 ohms. Right? So that tells us that the parallel combination of bulbs B and C could be replaced with a single bulb of resistance 2 ohms. So if I do that, sort of in redraw what the circuit effectively is at this point, this is the replaced one, and this is still bulb A. And now we can see that there's a series combination. So the resistance of bulbs A and that BC combination is going to be the resistance of A, 3, plus the resistance of that BC combination, which is 2, which is 5 ohms. And that now is the equivalent resistance of the circuit. So now we can use Ohm's law, which is that the total potential difference supplied by the battery, delta V, equals the total current that comes out of it times the equivalent resistance of the circuit. Or I is 9 over 5, or 1.8 amps. Right? So the key to this one is identifying sort of what parts of the circuit you can combine to simplify it until you get down to a single resistor that sort of is the same effect as all the old ones that you had. Alright, so that's part A. Part B looks like a very short question, but it's actually fairly long. And our question is to figure out which light bulb is the brightest. And the key here is that brightness is determined by the power dissipated. So we're going to have to be doing a calculation like that. But because of Ohm's law, right, this thing, we can rewrite the power equation in several different ways. Right? The AP sheet only has this one, but you can rewrite it. Right? If I replace delta V with I times R, then I get I squared R. Or I can replace I with delta V over R, and so I get delta V squared over R. So depending on whether we know current or potential difference, we can calculate the power dissipated. So the first one of these is very easy to do. The power dissipated in bulb A, we just got the current and we know the resistance. Right? I squared R. And we plug those in, we get 9.7 watts. Right? So that's one number we have. That's the power dissipated in bulb A. That's the thing you're going to need to compare to figure out what's the brightest. So for the others, we have to do a little bit more work with Kirchhoff's laws. Right? So I recognize that I know the current through bulb A, and then when we hit this junction, it's going to split, right, into two spots. So I'm going to have one loop, like so, and another loop, like so. And if I want to know the current through bulb B, what I really need to do is use that loop law to figure out the potential difference through across bulb B. And that'll be the same as the potential difference across bulb C, and then I can use this form of it. It'll actually be easier in calculating the current. So, loop law tells us that delta V loop is 0, or for that first loop, the A, B, and battery loop, we have 9 volts minus the voltage across resistor A, 3 times 1.8, minus delta VB equals 0, which tells us delta VB is 3.6 volts. Oops. Alright, so now we can use the power equation to calculate the powers in bulbs B and C. And they're not the same because the resistances are... So PB is 3.6 squared over 6, right? And that equals 2.2 watts. And PC, same potential difference because they're in parallel, but different resistance because they're different bulbs. And so that's 4.3 watts. So now we have the three powers, and we can compare. And we see that this bulb A power is much, much larger than the... And so we conclude bulb A is the brightest. Right? It is important to note that you had to address the power directly. If you just compared currents or just compared potential differences or voltages, then you wouldn't be able to fully show which one was the brightest, so you didn't get all the credit. You had to compare powers. Alright, and now our last part. We're opening switch S and we want to see what happens to each bulb. Right? So when switch S is open, our circuit becomes effectively this. Right? Bulb C is not even in the circuit at all anymore. It's not connected. So, what's the equivalent resistance of this new circuit? This is just RAB, and they're in series, so we add them up. 3 plus 6 is 9 ohms. Right? Our old equivalent resistance that we calculated to answer part A was 5 ohms. So our EQ goes up. If we use Ohm's law, delta V equals IR, this tells us that the current must decrease, right? The resistance went up. If the current has gone down out of the battery, because the current out of the battery and the current in bulb A are the same, that tells us that the current in bulb A decreases. Since the current in bulb A decreases, and P is I squared R, and we haven't changed its resistance, this tells us that bulb A, actually let's move that elsewhere, this tells us that bulb A is dimmer, not dinner. Okay, so that's bulb A. Bulb B, we need to do one additional calculation for. We need to figure out what the current through bulb B was before. Right? So bulb B, actually let's write it this way. So we know the potential difference across bulb B, that's this, 3.6 volts, and we know its resistance, so we can calculate the current using Ohm's law. Delta V over R equals I. So this tells us that IB before equals 0.6 amps. Now, because it's in series with bulb A, it gets the total current. So let's calculate what that new total current is using that equivalent resistance of 9 ohms. So delta V over R equals I. So this tells us IB after is 1 amp. Right? So we can compare these numbers. We see the current is increased, and then by the same reasoning here, bulb B must be brighter. Yeah. Okay, so now all I have to do is bulb C, and I don't really need to write anything for that. Bulb C is no longer connected to the circuit. It therefore has no current flowing through it, so it must get dimmer, right? In fact, it actually just goes out. Right, so that one's, I think bulb C is the really easy one. You'd better not miss that.